This video is going to address power and movement from Chapter 6, specifically electromechanical methods. So we'll be looking at automated systems and subsystems, mechanical systems, electrical systems, and rotary motion. Alright, so the main purpose of a power source is to supply energy to perform work. So we have some definitions here. The main purpose, like I say, is we're going to drive an actuator. So an actuator is a device that is converting that energy from the power source into motion. These actuators will typically give us either a linear or rotational motion. So some common types of actuators we talk about are motors, cylinders, solenoids, or ball screws. Alright, so this is just kind of a block diagram showing the kind of subsystems. We have our energy or power source, we have a transmission path, we have some type of control, and then we have some indicators and our load. So we have, we're trying to control movement of the load. We have to have some sensors or some indicators in here. So we have indicators connected so we can monitor how the control is handling the motion of the load. Alright. So the energy sources have several uses. Number one, of course, is to move the robotic arm. One is to actuate the production tooling, and of course we need power for the controller itself. So our three types of energy sources could be either hydraulics, pneumatics, or electric. Today we're going to focus primarily on the electrical. Okay. Alright, so the transmission path is a subsystem that's going to provide a channel for that transfer of energy. And when you look at a complicated system such as a robot, there's actually several different areas where we have to transmit that energy. So there might be several different types of transmission paths in a complex system. Alright, the load is referring to the part or parts that are designed to do the actual desired work. Okay. Control is going to alter that flow of energy so that we can control the type of work, control what's happening. Control devices operate within the transmission paths. Right. So as I kind of said, the load is referring to the part or parts that are to do the desired work. However, we also have losses. All systems are going to have some loss. Loss could be the electrical loss due to resistance in the wires, or mechanical loss due to resistance to more of a mechanical friction type resistance. Okay, that loss is undesired, number one, and typically that loss results in taking that energy from the power source and converting it into heat. Okay. So indicators is kind of a general term referring to the subsystem that's going to display, record, or report the operating conditions throughout the system. So when we look at our power classifications, we have electric actuators. Electric actuators kind of come in two forms. The first being electric motor, which we'll usually refer to as a servo motor. Servo motor actually means that it's a controlled motor. And motors, electrical motors, take that energy and convert it into rotational motion. Okay, so an electric motor or servo motor is going to generate rotational motion. All right. Another method, of course, would be linear motion. So we can take that electrical energy into linear motion. They have been working for many years on linear motors to move it, but a lot of times that this linear motion is actually created by using a rotational servo motor to drive a ball and screw type application. Okay, so we're going to discuss some properties of electricity here. So current, I've already mentioned current several times. Current is defined as the movement of electrons, or technically the movement of charge, but in solid materials that is done through electrons. And so we can have AC, which alternating changes directions, goes one way half the time, and then turns around and goes back the other way, or DC, which is direct current. All right. We can use something called rectification, which will rectify the AC current and change it to DC only. So remember, AC means it's going back and forth, and rectification then basically prevents it from going back in the other direction, so that it changes it so it can only flow in one direction. We also have things called inverters, which will take a DC, which is just going in one direction, and it'll invert it and send it back in the opposite direction, so we can turn it back into AC, where it goes forward for half the time and then inverts it and sends it in the opposite direction for the other half of the time. Now, to get these electrons to move, to get this charge to move, we have to push it. And voltage is the pressure or the force that causes those electrons to move. Okay. So current is effectively defined as electrons in motion or charge in motion. Current leaves the current is the same everywhere in a series circuit. So what that means is that the current leaving the power device is also, you're going to have the same amount of current entering into the other end of the power device. So if you have 5 amps leaving the top of a battery, 5 amperes leaving the top of a battery, you're going to have 5 amperes returning into the negative side of that battery at the exact same time. Okay, so current flows through an entire device. Okay, current in is equal to the current out. So as I just said, if I got 5 amperes flowing out the top of the positive of a battery at that exact same time, I also have 5 amperes of current flowing into the negative side of that battery. Okay, the unit for current is amperes. All right, and it's actually the current, it's the flow of that charge that can cause harm. Voltage is defined as a separation of charge. So you get a positive charge on one side, you get a negative charge on the other, and so you've got this separation of charges, and the opposite charges are attracted to each other, and that's giving you that force that where they want to come back together and balance the charge. So if you separate those charges, you create this pressure, this attraction between them, which they want to balance back out. And so the more you separate the charge, the higher the voltage you're going to get. Okay. All right, so the units for voltage is volts. All right, sometimes they also use the term potential difference or electromotive force, are other terms that they use for voltage. All right, an analogy of electrical energy or electrical power is with water. So if you think about a hose attached to a spigot here, you have pressure at the spigot, and when you open the valve, the water starts flowing. So with the valve closed, there's pressure at the valve, but there's no actual movement. So you have to actually open the valve. Similarly, with an electrical circuit, right, you have to close the switch to allow the current to flow. So with the water valve here, you open the water valve, and the pressure, the build-up pressure of the water then pushes that water through the hose and sprays out the other end. So the pressure is causing the water to move through the hose, and the more pressure you have, of course, at the end of the nozzle there, you're going to have a longer spray if you have more pressure. You're going to have more water coming out if you have more pressure. All right, so here's kind of a little drawing showing a battery. All right, and you see these electrons. All right, we already said that current is the flow of electrons, and technically those electrons leave the negative of the battery and come into the positive. So we talk about electron flow. Electron flow flows out of the negative of a battery terminal through the light bulb or whatever that it might be going in, and then returns back into the positive of the battery because it's electron flow. However, we use what we call conventional flow. Conventional flow says that the current is flowing from the positive of the battery to out the positive of the battery through the circuit to the negative of the battery. Alright, so we have several different types of actuator kind of devices shown here. The first one over here on the left is a heating element, and so that just simply takes, it's basically a resistive element. It takes the electrical energy and converts that into thermal heat energy. So it just uses it to heat stuff up. Right, this time of year, as it's starting to get colder, right, you might be using a small portable heater. It's exactly what you're doing. You're taking that electrical energy, running it through a resistor, and that resistor is converting the electrical energy into thermal energy. Another one, of course, is lights. Right, if we want to have lights, we flip the switch and the light comes on. So we're turning that electrical energy into light energy. Speakers, right? So you take that electrical energy, you move it through a magnet attached to some sort of flexible material, and you can produce sound. And then, of course, finally here we have motors, which we've already stated. Motors turn electrical energy into motion. Alright, there's lots of different voltages that you might see. We have here in the United States, of course, we use 110 or 120 volt power. Alright, and this kind of varies depending on exactly how we're getting that power, but we won't really go into that today. But they're basically the same voltage. But when we start talking about industrial type applications, they use what they call three-phase voltage, and a lot of times they use like up to 480 volts, or even the very large motors even use up into the thousands of volts to power those motors. Alright, so if we're trying to troubleshoot an electrical issue, okay, you need to kind of think that the current is going to flow from a high potential to the low potential. And if that current cannot flow, then it's said that the circuit has an open. So if the switch is open, you know, if you flip the switch and open the switch, then no current is flowing to the lights, so the lights aren't on. On the other hand, if the charge flows around the device we want it to go to and produce the work, if it's bypassing that, we refer to that as a short. So if you have a short circuit, you're basically bypassing all, or sometimes maybe just it's an internal short, so you're just bypassing part of the intended path. So you end up getting a high current flow, but it's not flowing through the device like you want it to, so you're not getting the energy where you desire that energy. Alright, so remember, it's the voltage that creates that electrical pressure and causes the current to flow. The flow of electrons is the current, okay, but we need that voltage to push it. Current in equals current out, so the current through a direct circuit, if it has no other path to go, it's the same everywhere within the circuit. Alright, so we can very easily test the voltage by using something called a voltmeter. Okay, this here is shown as actually what they call a DMM, a digital multimeter. It can actually measure voltage, both AC and DC voltage. It can actually also measure current, and a lot of these devices, like this one shown here, can actually measure other things such as the beta of a transistor and things like that. But typically these measure resistance, voltage, and current. But to measure current with a device like this, you would actually have to disconnect the circuit. But to measure voltage, we can measure voltage without actually disconnecting or cutting power. Okay. Ground is referred, you know, all electrical circuits will have a ground, which is 0 volts. Okay. Typical AC sources and controls is 120 volts. Typical DC sources for control applications, at least, is 24 volts. Okay. Already talked about an opener or short. Using block diagrams will help us follow the layout of the system or the subsystem, so we can kind of help troubleshoot where the issue might be. Alright, so as already kind of talked about, we need to transmit that energy. And so if we have an electrical motor, we'll have electrical wires connecting from our power source to the electrical motor. But the electrical motor then is going to give us mechanical motion, and so from there we have to have another system to drive the mechanics of it. So we can do that through what's either called a direct drive, where you pretty much attach the servo motor directly to whatever it is that you want to move, or a reduction drive, which allows us to increase the torque but at the cost of reducing the speed. Okay. So the direct drive, we can only get rotational or angular motion out of an electric motor, or at least a rotational motor, which most are. But it gives us a one-to-one relationship. Okay, so if we attach this to a robot joint and the motor is rotating at 10 revolutions per minute, that's the speed that that robot joint is going to rotate at. But with a reduction drive, which can be either a gearbox system or a belt and pulley system, okay, we can trade speed for torque. Okay, or you could go the other way. You could trade torque for speed, but most of the time we want to use a smaller motor, and so we gain torque by using the gearbox or the pulley system. So here's just kind of showing a gear, some different gear systems here. You have up at the top here, you have a straight bevel type system, and this is a good system. But if we went to a bevel gear, kind of shown here on the right side over here, the spiral bevel gear, we can increase contact between the teeth. So we have longer contact in the teeth, which gives us more strength at the connections. We can also, by adjusting the actual type of bevel on there, an advantage of this, like shown down here in the bottom right corner, is that we can offset the shaft. So you see, like these top two here, it's we have a 90-degree angle, so we're getting a 90-degree change in angle, but the shaft is in line with the center of the driven gear. But down here you can see that the driven gear is up at the top, so by changing the way the bevel is, we can also kind of shift where the shaft comes into the system at, which at times can be very, very useful. Okay. Over here on the left, we just have two gears that are directly connected. And so what happens here, if A is turning clockwise, then the B gear is going to turn counterclockwise. Alright, so here's some examples. We got the straight bevel gear down here, so you can see that it's actually got to be essentially perpendicular to the gear that it's driving. But as we start adjusting the bevels, we can go from to a hypoid to a spiroid, all the way up to what's referred to as a worm gear. And so if it's a worm gear here, we can actually be tangent to the gear we're driving instead of perpendicular to it. So again, sometimes it's very convenient by depending on where your driving shaft is at in the circuit. Alright, so how do we increase torque? Well, torque is your distance, okay? You have a force being applied, and so the torque is the force times the distance, okay? Or the force is torque divided by the distance. So if you take a smaller gear and drive a larger gear, what you do is you get this ratio down here. So you get this ratio where the torque of the second gear is equal to the torque of the first gear times the length of the second gear divided by the length of the first gear. And so you can very easily double your torque by doubling the size of this second gear. Okay, so we can double our torque. All right, here's just some images of some worm gears. Okay, these worm gears are very, they allow us to drive with the shaft at the top and to get the motion, so it gives you there. It also some examples showing you how we can do or you can use that angular motion to actually drive linear motion using something like this rack and pinion here, or this system here with this external ball return system. So this is actually turning the shaft with a motor, but then these ball bearings run along the threads of the shaft and allow you to get a linear motion out of this connection on top of here. Okay. Now there's a really interesting little website here shown at this link here. This guy provides this website showing you with the different gears, and he's actually got some simulation to that, but it's actually focused on creating gears by cutting them out for wooden out of wood for various applications and stuff. But it's the website kind of shows you, lets you change the different types of gears and the amount of teeth and various things like that. So it's kind of interesting to check out. All right, so when you look here, to lift very large loads, we need these reduction drive systems, because we're trading the speed. Electric motors can run very fast, much faster than we really need most of the time for automation needs. So we can make the motor smaller and then basically trade that speed for torque by using these various reduction drives. Okay. Now another type of system that we see used a lot is called a drive pulley system. Honestly, the drive pulley system, the difference between that and the gears that we were looking at is basically just the fact that by using the belt or chain, it allows us to spread the distance between the two gears. All right, so we can calculate the speed of the one wheel due to the speed of the other. All right, so we have like the velocity shown as v here is the radius of the wheel times the angular momentum. So the w there is actually representing an omega, which is the angular speed. So we have the velocity. So if we have a belt attached, the velocity right at the point where the belt leaves the one wheel, and at the point where the belt goes and just starts touching the top of the other wheel, that is going to be our linear velocity. And that linear velocity is the radius of the wheel times the angular velocity. And so we end up getting effectively the same torque sort of calculation that we had before. So we can get that the angular velocity of the second is equal to the angular velocity of the first times the radius of the first. Notice here, this is the radius of the first divided by the radius of the second. All right, so it's, and then if you wanted to calculate the torque that you're getting at wheel 2, it would actually be the exact same torque. The torque of the second one is equal to the torque of the first one times the radius of the second divided by the radius of the first. All right, so so this is showing the angular velocity here, W or omega. And if you wanted to calculate the torque, then the ratio between the radius R1 and R2 gets flipped over. So here we're our speed is slowing down, right? Our speed at W2 is slower than the speed of the first one because the radius 1 is smaller than the radius 2. So we're getting less speed but more torque. So here's the torque, kind of showing you the torque, okay, which is just the flip of the ratio. Okay, so there we get the torque of the second one is equal to the radius of the second divided by the radius of the first times the torque of the first. So your small wheel, if your small wheel is your drive wheel, it's going to give you a higher torque because you're driving a larger wheel. You're going to get more torque at the larger wheel, but your trade-off is you're trading speed. Alright, so here's just an example of a calculation for that then. So we have a pulley with a radius of 6 inches and a second pulley with a radius of 12 inches, and the drive pulley has a torque of 50 pounds. Alright, so our ratio is 12 inches to 6 inches, so it's a 2-to-1 ratio, and our driving wheel can output 50 pounds of torque, actually 50 foot-pounds, it should be foot-pounds there. And so we're doubling that because we've doubled the size of the wheel we're driving, so we get 100 foot-pounds. So we've doubled our torque, but again we reduced our speed by half. So it's a trade-off there. So these drive systems, we can increase our torque and our ability to drive heavier loads by driving them slower than we would if we used a direct drive system. So we lose speed but gain torque. We gain the ability to drive larger loads. We see this a lot with like bicycles. So if you have like a 10, 12, 18 speed bicycle, when you're trying to go uphill, you shift the gears so that you have a larger, so that your driven gear is larger than the gear you're driving it with, and that slows you down so you can't go up the hill as fast, but you have that extra torque for getting up the hill.